Let us talk about this problem. We are given two sorted arrays. We need to print all the elements of both the arrays in sorted order. Let's understand the problem with these examples. The first array is 10, 15, 20. Second array is 5, 6, 6, 15. So we need to print all these in sorted order. The smallest element 5, then 6, 2 times, then 10, then 15 2 times, then 20. In this example, we have 1, 1, 2 and then 3. So we need to print all these 4 in sorted order. Now please pause this video and try to write down a function that takes two sorted arrays as input and prints all the elements of both the arrays in sorted order. Here is a naive solution to solve the problem. Let's say we are given this array A as this and M is the length of this array B as this and N is the length of this array. What we do first, we create an array of size M plus N, right? We create an array of size 6 in this example. After creating the array, we copy the elements of first array into this array C. So I have created array C of size 6 and first I have copied the array A elements into the array C. Now we copy the array B elements into C. So our C array now contains both array elements, but they are not in sorted order. So what we do simply, we call the sort function on C array and we get the elements sorted order. So we have all the elements of A and B in sorted order in array C, and that's what we wanted. So we can simply traverse through array C and print it. So we'll get the output. Here is implementation of this. So this is C++ style syntax. In Java, you can create an array of size M plus N this way. Also in Java, you don't have to pass lengths as parameters. You can get lengths M as A dot length and N as B dot length. First thing we do is we run through the array A, we copy the elements of array A to C. Now we run through array B and we copy the elements after index M. M is the length of array A. This way we have all the elements of A and B in array C. Now we sort this array C, right? And this is syntax to sort in C++, this is the syntax in Java. After we sort, we simply traverse through array C and print the array C. Now what is the time complexity of this? See, you are sorting an array of size M plus N. So this is the majority of the time taken by this algorithm, which is M plus N into log M plus N because of the sorting algorithm. This is big O of M, or you can say theta of M, because it's always going to run M time. This is theta N, this is theta M plus N, but this is big O of M plus N into big O into log of M plus N. So this is the time complexity. We can ignore the lower order terms. That's what we do in asymptotic analysis. And auxiliary space is theta M plus N for this array. Now please pause this video and try to think of a solution that works in linear time, theta M plus N time, and requires big O of one auxiliary space. Let us now talk about idea for the efficient solution. The idea is this: we are going to traverse both the arrays simultaneously. We are going to use two index variables I and j. I to access array A elements, j to access array B elements. For example, if you have these two arrays, you will have I and j initially 0, which means you are currently referring to 10 and 5. So what you are going to do is, you are going to compare AI with BJ, right? Then there are two cases that we are going to handle. The first case is when AI is smaller than or equal to BJ, right? Which means BJ is either greater or equal. And the other case is when BJ is smaller, right? And we are going to write some code for these two cases, logic for these two cases, and let's understand the logic. I've written the question mark here for you to write the logic, but we'll easily get the logic by this example. So if I compare 10 and 5, and if BJ is smaller, right? BJ is smaller here, right? 5 is smaller than 10. So what should we do? We want to print both the array elements in sorted order, right? So what should we do? We should print the element 5, right? And since we have processed this element 5, we need to move ahead in array B. So we print 5 and we make j equal to 1. Now we are again going to compare 10 and 50, and now 10 is smaller. So what are we going to do? We are going to print 10 on the screen and we are going to move ahead in array A. So we print 10 on the screen, make I equal to 1. Now we are going to compare 20 and 50. Now 20 is smaller, so we are going to move ahead in array A and we are going to print 20. Print 20 and move ahead. Now we are going to compare 35 and 50. Now 35 is smaller, we are going to print 35 on the screen, and now we are going to make I equal to 3. When I becomes 3, it becomes an invalid index. It goes beyond the last index. So if any of the arrays goes beyond the last index, you need to stop the loop because you can't do the comparisons anymore. So you stop at this point, but you have not processed these two elements yet. So the idea is this. See, once you have traversed both the arrays simultaneously and you have printed some elements, you have printed these 4 elements, whatever remaining elements are there, they are always going to be greater than already printed elements. Like 50-50 are greater than these 4. And since the array A is sorted, array B is sorted, both the arrays are sorted, whatever array has remaining elements, those remaining elements will also be sorted and they will be greater than these elements which have already been printed. So what all you need to do is, you simply need to run a loop to print the remaining elements. Now you have the complete idea. Please try to fill the gaps here, what you will write here, and then try to write the complete code. So I've written the statements or expressions when AI is smaller than equal to bj. I'll print AI and do I++. That's what we did here, right? In this case, we'll print bj and do j++. Now, why do we have equal to sign here? See, this merge function that we are going to discuss is stable also. If you have two elements, right, and if you have, say, this also 50, then array A element would appear first in the output. This will be ensured if I put equal to sign here. See, I can remove equal to sign here from here, then it will not be guaranteed that in case of equal occurrences, array A elements will appear first. And stability is important in sorting. We are going to discuss, we are basically discussing this logic for merge sort, merge function, right? And merge sort is stable. So this equal to sign, that's why is put where when A is smaller, so that you process array A elements in case of equality also. So now please pause this video and write down the complete code yourself. Here is complete implementation of the algorithm. We have written a merge function that takes array A, array B, M and N as 4 parameters. We initialize I and J as 0. We run a loop while I is smaller than M and J is smaller than M. See, the point is we want to come out of the loop as soon as we reach at the end of any of the two arrays, right? So I should be smaller than M and J should be smaller than N for this loop to run. And inside this loop, we have the same logic that we just discussed. If AI is smaller or equal to bj, then we print AI and move ahead in array A. Otherwise, we print bj and move ahead in array B, right? For example, here we compare 10 and 5. 5 is smaller, bj is smaller, we make j equal to 1. Now we compare 10 and 50. 10 is smaller, we print 10 and make I equal to 1. We compare 50 and 20. 20 is smaller, we print 20 and I equal to 2. We compare 50 and 50. 50 same, right? So we fall into the this if case. See, again I'm telling you, equal case is used to ensure that the first array elements appear first. In the merge sort implementation, we are going to pass first half of the array and second half of the array to this merge function, right? So we want to ensure that the first half equal elements should appear first. That's why we have equal in the merge. So we are going to print 50 in this case, and we are going to move ahead in array A. So I now becomes 3 and I has reached last index. I has reached beyond the last index. So we come out of the while loop. When we come out of the while loop, we have 2 more loops and we'll always execute one of these 2 loops. We'll never end both of them, right? In this case, we are going to execute this loop while j is smaller than n, right? Because we have right now j as 1, right? And we have elements to process in array j, these 2 elements 50 and 50. So we are going to run an iteration here for j equal to 1, and we are going to print 50 and then we are going to make j equal to 2, right? Then we are going to run one iteration, 50 and make j equal to 3. Now j becomes invalid, so we come out of this loop as well. So this is how this function works. Now, how does this function always work? See, if you are at index I in array A and at index j in array B, and these 2 arrays are sorted, that's our primary condition. Now, if I just compare these 2 elements and I simply process the smaller elements, that will be the next element, because all the elements after this are going to be greater than this, and all the elements are after this are also greater than or equal to this. Here also greater than equal to this. We allow equal elements also. And if AI is smaller than bj itself, then it's going to be smaller than all these elements also and all these elements also. So we can safely print AI. And the same thing applies to bj. That's how this algorithm works. And talking about the time complexity of this algorithm, if you see in this loop, we are either incrementing I or we are incrementing j. And what is the range of I from 0 to m minus 1, and what is the range of j? 0 to n minus 1. So we are incrementing one variable which lies in range from 0 to m minus 1 and another variable which lies in range 0 to n minus 1. So the total range size is going to be m plus n only. And we are going to moving ahead in this range by either incrementing I or incrementing j, right? So the upper bound on this time on the number of iterations is obviously m plus n, and it will not run m plus n all the time. For example, it did not run m plus n all the time. 2 elements were there to process, and the remaining elements are processed. So if you see overall the running time of this loop, it's proportional to m plus n, right? Whatever extra elements, remaining elements which are not processed here, they will be processed by one of these two loops. So the time complexity clearly is theta of m plus n. I'm using theta notation because it's exactly m plus n. You are going to run m plus n times, right? Theta m plus n times, 1 or 2 extra do not matter. And auxiliary space is clearly big O of 1, right? We are not using any auxiliary area here. We are simply printing the elements.